Hello everyone, welcome to Delphin. Today we'll be looking at basics of kinematics by specifically focusing on motion in a straight line, which is also known as rectilinear motion. We'll start by defining some of the key concepts by understanding what we mean when an object is at rest or at motion, and why it is important to define a frame of reference when mentioning that an object is at rest or in motion. Once we have that nailed down, we'll look at how we measure how much an object is moving by understanding the concepts of distance and displacement. After that, we'll look at how to measure how fast an object is moving by understanding the concepts of speed, velocity, and acceleration. Once we have those variables defined, we will look at how these variables are changing with respect to time, specifically looking at velocity time graphs and position time graphs. And we'll use those graphs to look at or derive the kinematic equations. So let us start by a quick question that I have for you guys. And this question was raised by Galileo. So let us say there are two objects I have. One of them is a rock, which is extremely heavy of 5 kgs, and the other one is a leaf. I have both of them in a completely isolated system, meaning there is no atmosphere. I release them both at the same time from a particular height of h. And the question for you is, which object reaches the ground first? Now, this question is really important because it is by understanding the motion of falling bodies that a lot of foundation of kinematics was laid down. So I'm going to give you the answer to this question at the end of the video, but it's something that you guys can ponder upon until then. All right. Now let us start by first defining or understanding what we mean by rest, motion, and why it is important to define a frame of reference. So rest is generally defined as when any object does not move or change its position with respect to time, meaning it is stationary. Similarly, opposite to that, motion is when any object moves or changes its position with respect to time. Now you can see I have written down you need to specify within a defined frame of reference. So why is that important? Let us try to understand that by an example. So I have an example for you. Let us say there is a person who is sitting on his chair, and there is a book in front of that person, and that book is lying on a table, right? And since the book is not moving, we would say that for that person, the book is at rest. Now let us say there is another person who is on the moon, and he, using a powerful telescope, is able to see this particular book in this guy's bedroom. But he concludes that the book is moving because the earth is moving with respect to the moon. So I hope you're understanding, or you're able to see why it is important, or the point that I'm trying to get to, and why it is important to understand or define the frame of reference. Because depending on the viewer, any object can be at rest or it can be in motion. Meaning, the frame of reference which is convenient to viewer or depends on the viewer, that one viewer can say that any object is at rest and the other can say it is in motion. Hence, it is only when we have a viewer that is meaning to saying that an object is at rest or in motion. So how do we define or represent a frame of reference is the real question then. Well, we generally represent a frame of reference by defining an XYZ coordinate system and saying that a particular position of an object in this particular frame of reference that I'm choosing is x, y, z. Now it can happen that one frame of reference is moving with regards to the other frame of reference, and we'll see that in the advanced section of the videos that I'll put forward, but it is still an important concept to keep in mind. So what do we mean by frame of reference? We can look at the definition that I have for you guys over here. As it is a system of geometric axes with a clock constituent in relation to which, with a clock constituent meaning there is time involved as well, in relation to which measurement of size, position or motion can be made. Let's go over that again. A system of geometric axes with a clock constituent in relation to which measurement of size, position, or motion can be made is what we mean by a frame of reference. Now, let's move on to understanding how we measure that a motion has taken place, or how much motion has taken place. Let's quickly define the concepts of distance and displacement. So let us say, and it is much more easier to visualize this on a map, on a two-dimensional map. So let us say there are points A, B, C, and D. And there is a person who moves from point A to point B. Then from point B, he or she goes to point C. Then from C, he or she goes to point D. All right. And in this scenario, someone comes and asks that person, how much distance have you traveled? How do you calculate that? Well, a quick way, we'll calculate that by first understanding what we mean by distance. So distance is the length of the path traveled by any body between its initial and the final position. It is a scalar quantity. All right. So in this scenario, distance would be nothing but the length of the path traveled from the initial position, which was A, to the final position, which was D. So the distance would be nothing but length of path AB plus length of path B to C plus length of path C to D. And distance can only be positive, meaning the length of the path traveled can never be negative. Now, what do we mean by displacement? Well, displacement is nothing but it is the shortest path that could have been traveled by this person. The way we define displacement, though, is by saying that it is the line connecting the initial and the final position whose magnitude is the length of the straight line itself. Now, it has both magnitude and direction. And the way we calculate distance is by subtracting the initial position from the final position. And we'll look at some of the examples to understand that. But let us come back to understanding what is displacement in this case. It is the line connecting the initial position, which was A, and the final position, which was D. So the line AD is the displacement. Line AD. Something for you guys to understand that would make it much more easier to understand this concept is, well, in order to calculate distance, you need three things. You need to know the initial position, you need to know the final position, and you need to know the path that is taken by the object or any person. Whereas for displacement, the only things that you need to know are the initial position and the final position. It does not matter what path has been taken by any particular object. All we care about is the initial position and the final position. Displacement is equal to final position minus the initial position. And distance is nothing but just adding all the paths that you have, length of all the paths that you have, that any person has traveled. Moving on, in order to understand how fast an object is moving, we need to factor in time. We do it in two ways. The way we factor in time is by doing it in two ways. First is by speed, by defining speed, which is nothing but total distance traveled by total time, and velocity is nothing but total displacement by total time. Let us look at the definitions. So an average speed is said to be length of the total path traveled divided by the total time interval during which the motion has taken place. An average velocity is when there is change in position or change in position or displacement divided by total time interval during which the motion has taken place. Acceleration is something that we say as the rate of change of velocity, meaning acceleration, is nothing but delta v, or change in velocity, by the total time during which the change in velocity has taken place. An acceleration is again something that was defined by Galileo, and it was something related to the same example that I have here for you guys. Initially, it was believed that when an object falls, any object falls, they have a constant velocity. However, it was Galileo who understood the motion of the objects in the right manner. He said it is not the velocity that remains constant, it is the change in velocity that remains constant. And he coined this term of change in velocity to be acceleration. And of course, when an object falls, the acceleration is nothing but the gravity. All right, so let us look at a quick example that I have here. A car is moving along a straight line, say O to say OP. It moves from O to P in 18 seconds. All right, so it goes from O to P in 18 seconds and returns from P to Q in 6 seconds. So it comes back from P to Q in 6 seconds. What are the average velocity and speed of the car in going from O to P? So the first case is O to P. So what is we need to understand, and the second part is from O to P back to Q. So we need to first calculate distance and displacement. So let's start by calculating distance. In this case, in the first case, the object is moving from O to P. So the distance is OP, which is equivalent to 600. And the time taken is equal to 18 seconds. So the speed is nothing but 600 divided by 18 seconds, which is equivalent to 33.33. All right. Now you need to also calculate the velocity, which is nothing but displacement, which is equal to final position minus initial position, which is equivalent to 600, which is final position, minus the initial position, which was 0, making it 600. And again, the time is 18 seconds. The speed is, velocity is 600 divided by 18, which is also equivalent to 33.3. All right. Now let us look at the second case, which is B. The car comes back from P to Q in 6 seconds. What is the, again, average velocity and average speed? In this case, the initial position is O and the final is Q, right? So the distance traveled is nothing but O to P plus P to Q, which is equivalent to 600 plus 200, making it 800. The time taken is equal to 18 seconds plus 6 seconds, which is equivalent to 24 seconds, making speed equal to 800 divided by 24, which is again equivalent to 33.3 meters per second. Now, the displacement over here is equivalent to initial position, final position, minus initial position, which is nothing but 400, which is the final position. The final position is Q, which is 400, minus the initial position, which was 0, making it 400. All right. The time taken, it would be the same, which is 18 seconds plus 6 seconds, equivalent to 24. Therefore, velocity is equal to 400 divided by 24, which is equal to 16.6 meters per second. All right. So I hope that example makes a bit more clear what we mean by distance and displacement. I have another example for you. Let's say in something similar, right? There is an x-axis and there is an origin, minus 100, minus 200, minus 300. There is 100, 200, 300, 400, right? So you have over here point A, B, and C. This is the origin, and there is point D and E. All right. So we have seen what happens when an object moves or a person moves in the positive direction. We just saw how we calculate distance and displacement over here. My question is, let's start by, I would like you guys to understand what happens to distance and displacement when it moves in the negative direction. So let us say the person moves from origin to point D, O to D, and then the person goes from D to E, and then the person comes back from point E back to D. All right. So what is the distance and displacement in this scenario? Well, distance is nothing but the length of path from O to D plus D to E plus E to D, right? And displacement is nothing but final position again minus the initial position, which is nothing but final position is what? Minus 100, right? And the initial position is 0, making it minus 100 meters as the displacement, whereas distance over here is nothing but the length of O to D, which is 100, plus D to E, which is 200, plus again D to E, E to D, which is 200, making it 500 meters. All right, so that was just a quick concept. I wanted you guys to also see what happens when an object moves in the negative direction, what happens to distance and displacement. And when you kind of want to factor in, you want to calculate speed or velocity, you just divide it by the time that it might take in order to move in either of the directions. All right. So let us move on to the next topic. But before we move on, I have another question for you. This is a bit more advanced and it is not specific to motion in a straight line, but I think you guys will understand it as well, or you guys can solve it as well. So the question is, there is a clock which has a minute hand of 4 centimeters long, right? So this is 4 centimeters long. Find the average velocity of the tip. Find the average velocity of the tip of the minute hand between 6 a.m. to 6:30 a.m. So at 6 a.m. it would be somewhere over here, and at 6:30 it would travel all the way and it would come back somewhere over here. And between 6 a.m. and 6:30 p.m. what would be the average velocity? All right. So it's a quick question for you guys to solve. Let me know what you guys come up with. Of course, I'll post the answers to that question as well in the video description below. All right. So let us look at or try to understand position time graphs and visualize how different variables change with regards to time. All right. So let us look at position time and velocity time graphs. Sorry. So let us say let's look at the first scenario, which is an object has no velocity and it has no acceleration. All right. So in that kind of a scenario, let's say there is a straight line and this is the origin. All right. And the object is just standing over here, or the person is just standing over here at the origin. All right. So the position, as you can see, is 0, which is the x. The velocity is 0 as well, because we are looking at a scenario where there is no velocity and there is no acceleration as well. All right. So what would happen with regards to time in this kind of a scenario? Well, in case 1, the position time graph would look something like this. So it is at position 0 and it remains constant at that particular position. All right. Let us look at another scenario where velocity and acceleration are 0 as well. All right. But instead of being at position 0, this person is at position 40. And we don't know how that person reached over there, but in this frame of reference that we have, that person is at 40. All right. So and the velocity is again 0 and acceleration is 0 as well. So how would the position time graph look like under this scenario? Well, it would be nothing but at 40 you have a constant line showing that that particular position is not changing, and it is at 40 meters in our frame of reference. All right, so then what happens? How does the velocity time graph look like under both of these scenarios? Well, under both of these scenarios, you can see that the velocity is remaining 0 throughout. So velocity would be something that remains at 0 irrespective of what time it is. So it's remaining 0 even with increase in time or change in time. All right, so let us move on to the second scenario that I have, which is there is constant velocity but there is no acceleration. All right, so what would happen in that scenario? Well, you can see I have written a constant acceleration of 5 meters per second, and so one of the quick things to keep in mind is, well, even though there is no acceleration, that case itself is a subset of when you have constant acceleration. So we'll look at constant acceleration later on, but over here you have a constant acceleration of 0 meters per second square. All right, so that is the only difference. So there is no acceleration, and the position, the velocity remains constant, and the position is changing as well because the velocity is changing. All right, so without change in velocity, there is no change in position. So the position is changing. So what would the position time graph look like under this scenario? Well, let us try to draw that. Right, so you have time on the x-axis 0, 1, 2, 3, 4, 5, 6 time, and you have 5, 10, 15, 20, 25. All right, so let us try to plot these points. So at time 0 we have it at 0 meters, so it is somewhere over here, right? At time 1 second you have it at 5 meters per second, 5 meters, so the position is over here. And I've deliberately chosen 5 meters because it's much more beautiful and easier to calculate, but you can try other numbers as well. So at 2 seconds you have it at 10 meters, so at 2 seconds you have it at 10 meters. At 3 seconds you have it at 15 meters, right? And at 4 meters, so this is 15, yep. And then at 4 seconds you have it at 20, right? So that is somewhere over here. Now when you plot the other ones as well, other points as well, the kind of graph that you'll be able to see is something that would be a straight line, and this would be a graph for constant velocity. Well, how would the velocity time graph look like under this scenario? Well, since the velocity is constant, velocity time, this is probably the worst one I've ever drawn, but velocity remains constant at 5 meters per second. So let us say this is 5 meters per second, and the velocity remains constant with respect to time. Let us look at the third case, which is more interesting case, where we have an increasing velocity and a constant acceleration. Let's try to plot first the position time graph, and I have already drawn a graph over here. Let us look at the position change with respect to time. You can see at 0 seconds it is at 0 meters. All right, at 1 second it is at 5 meters, so at 1 it is at 5. And sorry about the unevenness, but I think we'll manage. Unevenness of the distribution of all these numbers, but yeah, I think we'll manage. So at 2 seconds we are at 12 meters, so let us say the 12 meter is somewhere over here. So somewhere over here, right? Yep, 12 meters. At 3 seconds you are at somewhere 21 meters. All right, so 21 is somewhere over here. It's definitely somewhere over here. Okay. At 21 meters, at 4 seconds you are at 32 meters, which is right here. Sorry, right here. Wait a sec. At 4, oh sorry about that. Yeah, 4 meters is over here. Cool. Yep. At 5 you are at 45, so 45 is somewhere even higher, that is somewhere here. And yeah, we're going out of the space, but you can see like when there is a constant acceleration, the position time graph kind of is something like a polynomial, because it is kind of related to time by x squared. So you can see like a curve rising, right? So that is how the position time graph would look like. Let's try to plot the velocity time graph under similar scenario. So there is velocity time, you have it 1 2 3 4 5 and 6. You have 5 10 15 20. All right. So let us look at some of the numbers. So at 0 seconds, you have it at 5 meters per second. That is the velocity as 0. So this is 0. At 1, you have the velocity to be at 7 meters per second, which is over here, which would be somewhere, let's say, here. So at 1, you have it at 0 or 7 meters per second. At 2, you have it at 9 meters per second. So 9 is somewhere here. At 3, you would have it at 11 meters per second, which would be somewhere above here, right? And at 4, you would have it at 13 meters per second, which would be somewhere here, right? So as you can see there, when acceleration is constant, the growth in velocity would be constant, and again in this scenario, velocity would be something like a straight line. All right. Okay, so I hope you are able to see how the velocity time and position time graphs manifest under different scenarios. This is when you had a constant zero velocity. This is when you had a constant velocity, and as you can see, the velocity is constant. And in the third case, we looked at what happens when the acceleration is increasing and the velocity is or the position is accelerating, or velocity is accelerating. Sorry, so the object is accelerating. All right, so this is how the position time graph looks like under all these scenarios. I would encourage you guys to look at what happens when the acceleration is negative. All right, so what happens when acceleration is negative, what happens when the position is positive and the acceleration is negative, and try out different scenarios and see how this specific graph manifests itself. All right. Cool. So let us come to the even more fun part, I guess, which is understanding or deriving the kinematic equations. Let's try to derive the kinematic equations. We have, by using this graph, we have a graph where there is a graph of velocity time graph where there is a constant acceleration. So it is similar to what we had previously drawn, where velocity is changing at a constant is changing uniformly with regards to time. And let us start. So as you can you can see that there is an initial velocity of an object, and then there is a final velocity of an object, right? So the way we represent, or we're going to call these variables, so the initial velocity, we are going to represent that by initial velocity, we are going to represent that by u, and the final velocity, we're going to represent that by v. All right, so using those kind of variables, we are going to try to derive the kinematic equations. So let us begin. All right, so let's start by first calculating the change in velocity that is happening. Okay, and because in order to calculate acceleration, you need to know change in velocity. So and it is kind of built into the definition of acceleration. So let us look at the distance between BD, the distance between BD, the length of this particular BD can also be equivalent to BC plus CD. All right, and you can see BC is nothing BD is nothing but the final velocity that we have defined. So it is nothing but V, and BC, which is the change in velocity, because if your initial velocity is u and your final is v, BC represents the change that has happened. All right, so BC is the change, and plus CD is nothing but the initial velocity, right, which is u, because CD is equivalent to OA. So CD can be written to OA, equivalent to OA and BC, and OA is nothing but U. All right, so V is BC plus U, BC is nothing but V minus U, right? So you can take U on the other side and you get the change in velocity to be the final velocity minus the initial velocity. Now acceleration is nothing but change in velocity over time. So you get change in velocity to be V minus U by time, all right, which is nothing but change in velocity over time, right? So that is how you represent acceleration. So let's mark this as 1, and then you kind of reshuffle the variables. You get V minus U is equal to AT. You take this T over here, and that is your first kinematic equation. All right, so this is the first kinematic equation. All right, so let us try to derive the second equation now. And what we want to do for the second equation is derive a relation between position and time. So what we're going to do is, let's say, and the way we do that is, you can see the relation that we have is already established is V is equal to nothing but change in position by time, delta x by delta t. So delta x is nothing but change in velocity, it is the velocity times the change in time. So meaning that if you calculate the area under this graph, you will get the change in position, or the position of an object, right? So in order to calculate the area under this graph, what we're going to do is we're going to split the graph into two. First is we're going to look at this particular triangle, and we're going to calculate the area of that particular triangle, and we're going to calculate the area of this rectangle. All right, so let us begin by calculating area of the rectangle. Area of rectangle is nothing but you can see it's nothing but CD times, which is length times height. So it is OD times CD. All right, so that is equal to OD times CD, and OD is nothing but the change in it's the time times CD is nothing but the initial velocity. All right, so CD is nothing but the initial velocity, so you get U and U times T. All right, area of triangle, so this is a triangle, sorry about that, I'm gonna just write triangle, is equal to half B times H, and it doesn't matter what your base is. So let's say this is your height and this is your base, right? So your height is nothing but OD again, so you get half times OD, and your breadth is nothing but BC, which is change in velocity as we have seen before, right? So you get half times BC is nothing but change in velocity, so you have V minus U, and OD is nothing but time itself. All right, so the change in position is change in position is nothing but or the position is nothing but area of triangle plus area of rectangle. All right, so area of triangle is half V minus U times T, plus area of rectangle is UT. All right, V minus U is, as we already derived over here before, is V minus U is AT, so you get half AT times T plus UT. Just rearranging these terms, UT, I'm bringing this before, so you get UT plus this one is half AT square. All right, so you get position is nothing but UT plus half AT square, and this is your second equation of kinematics. This is your second kinematics equation. All right, so let us derive the third equation now. The way we derive, again, so let me just clear these diagrams so it's easier for you guys to have a look at them. But the way we derive the third equation is, again, you can have a look at, there are two ways of deriving. So you can have a look at the area of area again under the line, and instead of calculating it by adding area of rectangle and area of a triangle, what we're going to do is we're going to add or we're going to simply calculate the area of this particular trapezium, all right? And the area of the trapezium, and is nothing but area of trapezium would be nothing but, again, the change in position, or the position, which is, so the trapezium is OABD, and the area of trapezium is given by adding the two bases, that is OA and BD. So you add those two bases, that is OA plus BD, and then you multiply that with the base, which is again OD, right? And you divide that by 2. So OD multiplied by OD divided by 2. So I'm just going to zoom it out. It's going to be much easier. Yeah, that was stupid of me. So OA, as you can see, is nothing but our initial velocity, which is u, plus BD is nothing but our final velocity, which is v, right? OD is again the time divided by 2, right? So x is equal to this. So time, again, you can write time as using this first equation, as you can see over here, which is v minus u by a, v minus u by equal to at. So let me just write it over here. V minus u is equal to at. You can write time as v minus u divided by a, right? So you can replace this time by this value. So you get u plus v divided by 2 times the time, which is v minus u by a. This would be equivalent to the position x. So x is equal to nothing but, you can just jumble around, you get v square minus u square divided by 2a, right? So 2 times a is 2a in the denominator, and in the numerator you have u plus v minus u, because u plus v, or v plus u and v minus u. So using the formula of a plus b times a minus b is equal to a square minus b square, you get, I'm going to write it much better, v plus u, you get v square minus u square equal to 2as, all right? So that is 2ax, right? So you take this over here, you get v square minus u square equal to 2ax, right? So this is the third kinematics equation, all right? There is another way of deriving it, which we will look at. So the way we'll do that is, so instead of, let's just start from here again, right? So let's take the area of triangle and area of rectangle again. Okay, so you have x is equal to, sorry, I'm going to write it with a black pen. X is equal to half v minus u times t plus ut, right? We're simply going to open the bracket. So you get half vt minus half ut plus ut, right? Which gives you take this and this term, you subtract half ut from ut, you get half vt plus half ut. You can isolate the values, you get half v plus u times t, right? So again, you take the t value from here, which is v minus u by a, half v plus u times v minus u by a, you get nothing but v square minus u square, 2a is equal to x, and you get v square minus u square equal to 2ax again. So there are two ways of deriving the formula. One of them is by calculating the area of the trapezium, and the other one is just using the area of rectangle but just expanding the values over here. All right, so those are the three equations. And I'm going to clean the board and we can try to solve one of the problems that I have for you guys right here. All right, so I'm going to quickly, we have a question over here. I'm going to quickly write the three equations that we have derived. V is equal to u plus at, x is equal to ut plus half at square, and v square minus u square is equal to 2ax. All right, so these are the three equations that we have. Now let us come back to the question. a particle starts with a velocity of 2.5 meters per second along an x-axis and accelerates uniformly at a rate of 0.5 meters per second square. So the initial velocity u is equal to 2.5 meters per second, all right, according to what has been given to us. Our uniform velocity, the acceleration is uniform. A is equal to nothing but 0.5 meters per second square. What we have to find is the distance traveled in the first 3 seconds. Okay, so we need an equation that uses u and uses a, all right, acceleration, to find the position or the distance traveled, which is nothing but this equation. You can see we have u and we have a, and we also have the time, so that is in 3 seconds. All our units are also in seconds, meters per second, so we don't have to convert or do anything. So the first question's answer would be x is equal to, or the distance traveled would be equal to 2.5 times 3 plus half 0.5 times 3 squared, all right? And the answer to this would be 9.75 meters, all right? So your x is 9.75 meters. Okay, moving on to the second question. How much time does it take to reach a velocity of 7.5 meters per second? So now they have given us a velocity, or the final velocity, which is 7.5 meters per second. What they are saying is, well, you have the initial velocity, you have the final velocity, you also have acceleration. Tell me what is the time it would take to reach this much velocity, all right? So you have now the only equation which uses velocity, initial velocity, and the final velocity, and the acceleration are these, is the first one, right? So we're going to use that equation. V is equal to u plus at. We're going to substitute values. So 7.5 is equal to v is 7.5, u is nothing but 2.5 plus a is 0.5, right? Times t. We need to find this value. Okay, you're going to take this number over here. You get 7.5 minus 2.5 is equal to 0.5 times t. T is equal to 7.5 minus 2.5 is 5 divided by 0.5. You get the value as 10. All right, so that is the answer for the second question. All right, now let's look at the third part. All right, how much distance will it cover when it reaches the velocity of 8 meters per second? All right, so I wanted all of us to get used to the all these equations. So now the final velocity is 8 meters per second, and we have an initial velocity, we have a final velocity, sorry about that, and we have an acceleration. What we need to figure out is how much distance is covered. Okay, so what we don't have is the time. So the only equation that does not have time is this one. So you have v square minus u square equal to 2ax. We need to find the distance. So 8 square minus the initial velocity is 2.5 square divided by 2 times 0.5 is equal to x. 2 times 0.5 is 1, right? So 8 square minus 2.5 square divided by 1 is equal to x. I'm going to quickly calculate 8 square minus 2.5 square, which is equal to 57.75, right? So your x is 57.75 meters is equal to your x. So the distance traveled would be 57.75 meters. The time taken over here was in 10 seconds, and so that was the answer for the second question, and the first question's answer is 9.75 meters. Right? So I hope that helped. And before we close the video, yes, we still have to answer the initial question that I posed in front of you. All right, so which is over here. Now we have two different objects of different masses. Which one would fall first if there is no atmosphere, or which object reaches the ground first? And the answer to this question is hidden in the equations that we derived, which is v is equal to u plus at, v square minus u square equal to 2ax, and x, and x is equal to ut plus half at square. All right, So in the equation, you can see, like, you can use the initial velocity as zero, acceleration as the gravity, etc., and all of that, right? But one thing you will notice is that there is no mention of mass, right? So mass is not involved, or it does not matter what the mass of an object is. Irrespective of the mass, we are going to have the position of an object change. So it solely depends on the acceleration, right? So since the acceleration for both these objects are same, they should both reach the ground first, right? So in an isolated or they should both reach the ground together, right? So in an isolated system where there is no atmosphere, it doesn't matter if you're releasing two objects at the same height, they're gonna reach the ground at the same time, right? And if you want to do this experiment at home, one way you can do it is you can take two balls and make like a wooden block shaped of like a triangle, and then you release a sphere of two different sizes. What you will notice is both these spheres reach the ground at the same time. All right. So yeah, I hope that was interesting for you guys to learn. The thing that makes normally a leaf, well, we're going to look at all of that in future videos as well. But when you isolate the atmosphere, you kind of remove the friction or friction that is normally generated because of fluids. So that is why both the objects would fall at the same time. All right. So normally we're gonna look at motion of different objects in fluids as well later on, and there you will be able to see how the rates and how rates of two different objects and everything varies. All right. So I hope this video was helpful. I'm also going to share this particular definitions that we have and everything. You guys can of course work on the question that I have written down over here. I'll try to put together also a set of questions that you guys can solve. So yeah, thank you so much for tuning in, and I'll see you later.